So welcome to the last part of lecture 1. This is our third part. So I want to just kind of finish up by talking about some more notation. So a lot of what we're going to do in this course is looking at f to the n. Now we don't want to be writing out n tuples all the time. It gets a little bit cumbersome to do that. So in the book or in the course, what we're going to do is we may just simply write x as an element of f to the n. Okay, so what you want to do is you want to pay attention to the context. Okay, so when I write x as an element in Fn, right, this tells us that x really is in some sort of n tuple, x1 through the xn. Right? And so this is also important when you think about when we write something like 0 inside of Fn. Fn is a collection of n tuples, but 0 doesn't look like an n tuple, right? But what this really means is that we're thinking of 0 as the vector containing all, or the n tuple containing all of zeros. So this means the set as a list. So you have to pay attention to how the elements are being used. So when I write x inside of Fn, it really is telling me, oh, there's a whole list there in the background. Same thing with 0. If 0 is inside of Fn, that means I'm looking at the list containing all zeros. And just to kind of give you kind of a sample of kind of using this notation, here's kind of an exercise or an example where we're going to show that if we take lambda times x plus y is equal to lambda x plus lambda y for all x and y in f to the n and lambda in f. Okay, so when you're reading this, you want to note that x and y here are really being used in kind of in a compact way. They're really telling us about lists, n list or n tuples. Okay, so let me show you how the proof would go. Right, so you would go something like this. So since x and y are in Fn, we know that x is equal to some sort of n tuple, and y is also equal to some sort of n tuple. Okay, so this is good because now we can actually manipulate the particular objects that are in our set. So let me go over to a new page here so I have enough room to do the proof. Right? So I'm interested in knowing what is lambda plus xy. Right? Well, then I can substitute in what x and y are. So x is the n tuple, x1 up to xn, and I'm adding that to the tuple y1 to yn. So and now what we want to do is we want to add the tuples x and y, right? So we know how to do that by the definition of scalar, by the definition of addition of this. So this gives me x1 plus y1, x2 plus y2, up to xn plus yn. So that's my new n tuple. And now I'm taking a scalar and I'm multiplying this n tuple, right? So here I would have scalar multiplication. So here I would get lambda times x1 plus y1, lambda times x2 plus y2, up to lambda xn plus yn. But now in the first coordinate, I can break this up, right? Because this is just a number inside of f, right? So let me give myself some more room. So I can think of this as lambda x1 plus lambda y1. That's in the first coordinate. In the second coordinate is lambda x2 plus lambda y2, all the way to lambda xn plus lambda yn. So this is the property of f. And what we notice is then, well, I can break this apart and think of it as the sum of two n tuples, right? This is the same as lambda x1, lambda x2, up to lambda xn plus the n tuple lambda y1 up to lambda yn. And notice that I can now factor out the lambda, right? So I get lambda x1 up to lambda xn plus lambda y1 up to yn. And this n tuple, right, is represented by x. And this n tuple, y1 up to yn, is represented by y. So we have lambda y. okay? And this is what we wanted to prove. I don't know if you can remember here. Let me just move back. Right, we were trying to show that for any n tuple x and y, lambda times the sum of x plus y is the same thing as lambda x plus lambda y. And that's what we have here. We have the first thing on the left-hand side and a bunch of justifications, and we ended up at the bottom, okay, which is what we wanted, okay, our conclusion. So remember, we usually put our little square at the bottom to kind of remind us that we've reached the end of our proof, okay. So it's fitting that I do a proof on the first lecture. And here, let me just kind of put this over here and make myself reappear. So just a couple remarks here. F stands for a field. Okay, I have mentioned this before, and R in the complex number are fields. Okay, but there are other examples of fields that you know. The rationals are also an example of a field. Okay, so actually any result that we prove in this class that uses F, it would actually hold for Q. But for this course, we're only going to focus on the real numbers and the complex numbers. So if you'd like to learn more about fields, a follow-up course, Math 3 GR3, which is abstract algebra, will be a place where you can learn about fields. But I've kind of listed in today's lecture all the properties of a field that we need. Okay, so just to kind of summarize for today, we kind of did a quick review of complex numbers, okay, and I introduced you to a field, F, and some of its properties, and we introduced the idea of Fn, which is a set of all ordered n tuples. So in the next class, or next lecture, part 2, we'll jump into vector spaces, which is kind of one of the key concepts in this course that we want to study. So I'll see you in lecture 2. Have a great day.